Let's do a little bit more discussion on vectors. I know that excites you to no end. What we want to discuss is looking at vectors in Cartesian components and polar components. And so we're going to start off by just assuming that I have some vector. So here's a vector A, and we're going to take a standard xy coordinate system. So my x-axis off to the right, and my y-axis going up and down. Then we've already discussed that I can take an x component of A along the x-axis. So there might be a component here, call that A sub x, and a component here, call that A sub y. And in the Cartesian system then, A is equal to A sub x in the I direction plus A sub y in the j direction. But in polar form, the vector A might be written as a magnitude of A, so you notice there's no arrow over the top of that, at some angle theta, where theta is always measured in the counterclockwise direction with respect to the positive x-axis. So if there's a negative sign in front of theta, then it's measured in the clockwise direction. But counterclockwise is positive, and it's always measured with respect to the positive x-axis. Now that doesn't mean we don't measure angles with respect to other axes like the y-axis or the negative x. But when I talk about a polar form, the angle theta is always measured with respect to the positive x-axis. So if you're measuring an angle with respect to some other axis, you're going to have to compensate. Now what we haven't discussed is the fact that if A is equal to A sub x in the I direction plus A sub y in the j direction, then the magnitude of A, which I might write the absolute value of A, or I'll just write it as A without the vector sign above the top, that's equal to A sub x squared plus A sub y squared, all under the radical. And this is just a restatement of the Pythagorean theorem. By definition, x and y are perpendicular to each other. And so the hypotenuse is the size of vector A, and the legs are A sub x and A sub y. And so the legs squared added together equals the hypotenuse squared. And so we just get this by using the Pythagorean theorem. In addition, if I look at theta, theta has A sub y at the opposite side and A sub x at the adjacent side. And so the tangent of theta is equal to A sub y over A sub x. And again, be careful what quadrant you're in, because if both A sub y and A sub x are negative, you're going to get a positive value. And so you're going to get the tangent of theta equal to some positive number. Your calculator is going to spit out a value of theta in the first quadrant, but in fact you're in the third quadrant. So be very careful about which quadrant you're in, and you have to think about what direction A sub x is and what direction A sub y is to know what that is. So I might say then that theta is equal to the arctangent of A sub y over A sub x. Now it's not uncommon for physicists and engineers to need to use an x and y coordinate system that's rotated. So for example, if I have an object sliding down an inclined plane, very often I'll have down the inclined plane as my x-axis instead of to the right as my x-axis. So if I have that same vector A that I had a moment ago, but now x is down in this direction instead of this direction, and y is then in this direction, always perpendicular to x at 90 degrees to the counterclockwise direction. This is still the same vector A, but what was at this angle theta with respect to the positive x-axis is now this angle theta with respect to the new positive axis. So if this is rotated through some angle alpha, theta has gone to a new value equal to the old value of theta plus this new value of alpha. So for example, if theta was 30 degrees, but I have rotated through an angle alpha equal to 15 degrees, then my new theta is actually equal to 30 degrees, the old theta, plus 15 degrees, which is 45 degrees. So given that I have a different angle theta, I'm going to have a different x component. It's still equal to A cosine theta, but this theta is not 30 degrees anymore. Now it's 45, or whatever it might be. And a new y component equal to A sine theta. Now the magnitude of A won't have changed at all, but if we look at that, if I write A squared equals A sub x squared plus A sub y squared, that's equal to A cosine theta squared plus A sine theta squared, and that's going to equal A squared cosine squared theta plus A squared sine squared theta, which is A squared times cosine squared theta plus sine squared theta But you know that cosine squared theta plus sine squared theta is equal to 1. Doesn't matter what theta is. So changing my angle does not change the magnitude of A. Same vector, same size. But the direction will have changed. So the x and y components are different, but their net magnitude is the same. And if I look at 3 dimensions, let's have x come out of the slide here. Y is to the right and z is up. And I have some vector A coming out in 3 dimensions. Recall that there is a projection of A onto the xy plane. That projection might be here. And there's still an angle with respect to the positive x-axis. I think I called that angle phi earlier on. I'm going to stick with that. This angle is 90 degrees. This side here is along the z-axis, so it's perpendicular to the xy plane. And I believe this was the angle I called theta. So if I draw perpendicular to the z-axis, I will get a component of A along the z-axis, and that's A cosine theta. And then this, which I referred to as rho earlier on, rho will be equal to A sine theta. In other words, it's the same as this over here, the same value, except projected onto the xy plane. So rho is equal to A sine theta. Then there is a component in the y direction, and that's rho sine phi, and a component in the x direction, and that's rho cosine phi. So A sub x is equal to rho cosine phi, but rho is equal to A sine theta, so this becomes A sine theta cosine phi. And A sub y is equal to rho sine phi. This should be a phi here. But rho is A sine theta, so this becomes A sine theta sine phi. Again, the z component is just A cosine theta. Get a real good idea of that if you actually pull out some string and tape it to the corners in your room and look at those x and y components and z components.